Okay, let me get started. I have a little bit of introduction to do before we get to the hands-on part. So we'll have a chance to wait for the network to settle down, because I think all the tutorials starting at the same time. That's part of the reason the network is slow. So we'll have a chance. And I have a couple of backup options if you're not able to get things set up. So, and we have some flash drives going around. So take it easy for a minute. Try not to get too distracted setting things up so that I can give you a little bit of background, and then we'll have time to get back to it. You'll be able to load up my slides eventually. This is the URL for the web page. And then you should eventually get to slides that look like this. So this is computational statistics using Python. I'm Alan Downey. I teach at Olin College, which is a new engineering school just outside of Boston. I see we have a couple of people here from Boston that I know. How many other Bostonians are out there? All right, good. Nice to see you all. Again, this is the URL. Here's some pictures from Olin College. Not everybody knows about it because it's new and small. Our mission is to fix engineering education. But that's not what we're going to do today. So today is about statistical inference. The three pieces of statistical inference are estimating the size of an effect, whatever the thing is that you're trying to measure, quantifying the precision of that estimate so that you can report how good the measurement is, and hypothesis testing, which I'll get to a little bit later on. We're using Python, obviously. You've come to the right place, and a little bit of pandas as well for doing the statistics. So this is an interesting time for the world of statistics. Just in the last 3 or 4 years, classical hypothesis testing has increasingly come under fire as not a good way to do science. And one of the reasons we know it's not a good way to do science is that we have increasing evidence that a lot of published results, things that passed a hypothesis test, are likely to be false. And that's partly a statistical argument. There have been papers about why that might be true, but also the replication crisis that you might have heard about, which is the effort to take a lot of well-known effects, especially in psychology. That's been one of the areas of focus for this, and just do the experiment again and see if you get the same results. And for a disappointing number of these attempted replications, it turns out that either the effect the second time around was substantially smaller or not detectable by statistical methods. So part of what I'm going to talk about today is, first of all, what is this? What is it supposed to be doing? What does statistical inference do when it works? And what is it that's gone wrong with the whole thing? The fundamental idea of all of it is that you have some population that you are interested in measuring. Sometimes it's literally a population, like a group of people, but often it's something else, animals or things or machines or abstract entities. So when you hear population, think, group of something. And sometimes it's not actually an existing population like everybody in the United States right now. It could be a more abstract kind of population like every person that could exist in a hypothetical world of a general model of a population. But this is the idea. You want to say something about a population, but you can't measure the entire population. You only have a sample. And so the inference part, the reason it's called statistical inference, is that you are inferring something about the population from something that you measured in a sample. And classic examples of this are things like drug tests and election polling, where you ask people who they're going to vote for, or you run a test between two drugs and you randomly assign patients to take one drug or the other, and then you get results like this. So the average self-reported pain score with one painkiller is 4.1. The average with the other drug, maybe it's the old drug, is 4.5. And it looks like the new drug might be better because the pain scores are lower, and low is good. But the natural questions you would want to ask are, well, how big is the effect? How big is the difference between the two drugs? How sure are we about the size of that effect? And can we say for sure that the new drug is better than the old drug? Or is there still some uncertainty? Is it possible that they're actually the same or that A is worse? So those are the three parts of statistical inference. How big is the effect? How sure are we about that? And is it possible that we're being fooled by chance, that what we're seeing is actually just random noise and we're seeing a pattern where there is no pattern. And that's the three things I'm going to talk about today in that order are effect size, measuring something and reporting usually a single number, that is how big it is, a confidence interval or a standard error, and they're usually equivalent to each other, just two different ways of representing the same information, is a way of quantifying precision. And you see this all the time with polling results. It'll be 51% plus or minus 2. And scientific results, we measured the thing and it was 1 kilogram plus or minus so many grams. So that plus or minus is a way of quantifying the precision of the estimate. And I'm going to emphasize the word precision because we're going to talk about the difference between precision and accuracy. You can have a very precise measurement that is not accurate. Now, precision is useful information, but it is not complete information. So I'm emphasizing that now, and we'll come back to it. And then the last part is a p-value, which you might be familiar with, which is a way of expressing how sure we should be that the thing that we're seeing, the thing we're measuring, is not just random noise. Just to get a sense of the room, I'm wondering how many of you are familiar with confidence intervals from previous work in statistics and familiar with p-values from previous work in statistics. Okay, great. So these are familiar ideas. Yes? Would I consider a college class to be familiar? Yes, you've seen these ideas. You've probably been given the conventional wisdom about what these things are, how they work, and how to interpret them. That's good. But I have to warn you that I'm going to be doing things that are a little bit unorthodox in two ways. One is a slightly non-conventional interpretation of these things. So I'm going to contradict some of what you probably learned, and I'll try to explain why I'm refining. Maybe I'm refining it, maybe not contradicting, but some refinement. And then the other is, and this is really the point of this, we're taking a computational approach to these ideas. The exposure that you had was probably mathematical. You probably did a lot of mathematical analysis. So, for example, when you computed p-values, you probably did things like t-tests, a student's t-test, or maybe a z-test. Are there other statistical tests that you remember learning about? ANOVA, chi-squared, f-test, student's t. Yeah, there's kind of an alphabet soup of these tests. More. Yes, but I'll get back to it. Or rather, yes, but I don't want to get into it. Although it was Guy Guinness, right? What? The guy was at Guinness Breweries?
It was this year, and he didn't, and when he published it in like the Statistical Journal, there's no internet back then.
All right, sorry, I regret asking. I don't want to get into it. Let's get back on. Sorry, so the p-values, all of that stuff that you learned were analytic ways of computing p-values approximately by using analytic methods, which were really important back when computation was expensive and hard. Computation has become effectively free, and what that means is that if you ever learned all that stuff, you are now free to completely forget it. Because there are simple computational ways to compute p-values that will save you from doing any unnecessary mathematics. Also, what's that? Am I talking about pseudo p-values? Let me come back to that. So part of what I'm going to get at today is when you're computing p-values, do it by simulation. You don't need analytic methods. Throw computation at the problem. It's usually very simple. Also, don't spend all of your conceptual and emotional energy on hypothesis testing, on p-values. When you report a statistical result, by far the most important thing to report is the effect size. If you tell me the effect size and nothing else, that's fine. We can all go home and be happy. Okay? If you want to go one step farther and give me a confidence interval or a standard error, that's nice. It is less important. It is a distant second. But it's nice. And one more step, if you want to go and give me a p-value in addition, that can be a little bit useless. I've described it sometimes in my writing as not completely useless. But it's pretty close to completely useless. dangerously close, and therefore is the least important of the three. You should spend as little time on it as possible. And that is one of my goals for this talk, is to spend as little time on it as possible. Here's why. I read a lot of papers where people lead with the p-value like it's the headline. Like, there's a statistically significant difference between these two groups. I don't care. That tells me almost nothing. What I really want to know is how big is the difference? I don't care whether it's statistically significant or not. Or rather, I don't care until you convince me that it's big. If it's big, then I might worry about a p-value. But telling me about a p-value and not telling me the effect size is pointless, and I'll give an example. This is a paper that drove me absolutely crazy a few years ago. Big headlines. This was a paper that was published in the Proceedings of the National Academy of Sciences, which is generally well regarded, and it was reported widely in the media. And it said that for girls in grade school, if their teacher was anxious about mathematics, they gave them a survey. They gave the teachers a survey to see how anxious they were about math. The teachers who were more anxious, their students would do less well on the exams. And if their teachers were less anxious, their students would do better. But it only affected the girls, not the boys. Okay, that's interesting. And if that's true, it's potentially something that we would want to fix. So this is very interesting. My immediate question is, how big is the difference? But they told me, oh, well, the p-value is 0.03. Not what I asked. What I asked is, how big is the difference? It wasn't in the media coverage, and it wasn't in the paper. So I read the paper and it says, okay, girls who are more math anxious, teachers are more likely to do worse. All right, I still don't know how big it is. I got the paper. There was nowhere in the paper that I could figure out how big the effect was. I had to go into the supplemental materials that were on the web page of the Proceedings of the National Academy of Sciences, and I had to crawl and find 3 different places in the paper where I could find out how big was the range in the anxiousness of the teachers, how big was the size of the effect between the least anxious teacher and the most anxious teacher, and that turned out to be about half a point. But of course, now I don't know what half a point is unless I know what the scale of the exam was, and that was in a 3rd place in the paper. When I finally pieced it together, I discovered that the difference between having the least anxious teacher on the scale and the most anxious teacher on the scale was half a point on a 100-point scale. Yes? Yes. Absolutely right. You're absolutely right. Let me just repeat it in case people couldn't hear it. You're saying, look, small is a matter of, is a relative thing. This might be small, or actually it might be big. You know, half a point could make a big difference. If we're talking about gambling and having a very small edge on the house, that could be the difference between making a lot of money or losing a lot of money. So big or small depends on context. Yes? Right. This doesn't give me the whole picture without the standard deviation. I agree, although you're being more specific by saying standard deviation. There are lots of ways to tell me how big it is in context, and that your choice will be different. Sometimes standard deviation is what I want, but not always. Good. All right. So punchline is, first of all, don't make me work this hard to find out how big the effect size is, and when you tell me what it is, give it to me in terms I understand and in a context that allows me to make sense of it, which is exactly what you were saying in the back there, which is great. All right, so I want to get into a couple of examples. This is our chance to play around with Jupyter. I'm going to do a couple of things here before you get into it. First step, I'm going to make you introduce yourselves to your neighbors so that if you're running into technical problems, you can get help with each other. That's going to be very important. So take a minute, shake hands, introduce yourselves, get things set up. I will resume in a couple of minutes. Okay. Now that you've met each other, your next mission is to launch Jupiter. And you have two ways of doing this. And there's the good way and the desperate, I hope this is going to work way. The good way is if you have Jupiter on your notebook, and if you have my repository, you have Jupiter on your laptop and you have my repository on your laptop, you're going to be running everything locally, and you don't have to depend on wireless, and that'll be good. Eric, who I should introduce, Eric Ma is helping out today, so thank you again, Eric, has the repository on that there USB drive. Everybody's good, okay. So launch Jupiter. The desperation move, if you're really stuck, this is the class webpage when things are not loaded properly, and this is a button that's not going to work. All right, let's run locally because the wireless is obviously not going to do it for us. If you don't have a working environment, work with your neighbor. What we really need is for every pair of people to have at least one working environment, and then you'll be all set. All right. So I'm going to have you launch the Jupyter Notebook, and the first notebook that you're going to open is called effectsize.ipynb. There's some reading there that I want you to do, and then the first exercise. And when you get to the part where it says stop here, what I'd like you to do at that point is stop there. Sir?
Do they work with Python 3 as well as 2?
Good question. The notebooks will work with either Python 2 or Python 3 without modification. If you have not launched Jupyter before, I'll just give you a quick demo up here. What I like to do is make sure that I've always opened a new tab, because now when I launch the server, it will grab the last window that I used and give me this. And I want comp stats and effect size. I have one, if you're using a Mac, you're not, but I'll get to your question in a minute. There's one thing I've discovered this morning, or I was told about this morning, which is that this matplotlib inline, if you are on a Mac, I have heard that that can get you into trouble unless you move it up. If you move it up to the top, you should be okay. So I'm going to run that. Forgot to turn my mic back on. So this is about taking an effect size and making it comparable in different terms. So if I tell you that there's a 15 centimeter difference between males and females, that will make sense to you if you know how tall human beings are. But if I'm talking about beetles, and I tell you that there's a zero .1 centimeter difference between males and females, your first question would be, well, how big are the beetles? And if I want to make comparisons across species, I can do that by expressing everything in terms of percentages. And this is not meant to be deep and profound, but just to get ourselves warmed up. So you can take the difference and divide by, for example, the male mean, and express it as an 8% difference. But part of the reason I set you up with this exercise is to make you realize that you had to make an arbitrary choice about what to put in the denominator. If you put the female mean there, you're going to get something slightly different, closer to 9%. And the alternative would be to take the total average human height and put that in the denominator. So there are a couple of different ways to do it. Really just a warm-up exercise. To summarize, simple difference in means is an obvious way to report effect size. A relative difference expressed as a percentage is a useful way to make effect size comparable across different groups. The drawback is just that you have to make a decision about what to put in the denominator. So let me get you back into the notebook. So finish up all the way to the bottom. Oh, no, sorry, take it back. I think there's another breakpoint in there. So keep reading, learn about Cohen's d, which is a way of measuring effect size, and then we will resume when you get to stop here. So while you all are working on exercises, I will often be up here doing a little bit of the exercise at a time. So if you get stuck, you can look up here and get a hint. To get you started, the simplest way to do this is to iterate through the male and female samples. They have already been randomized, so you can think of each corresponding pair as being a random pair. Okay, let's look over a solution to this. I wrote a version a minute ago that was using a for loop. If you're comfortable with for loops and list comprehensions, that's the way to go. The things that I've given you are also NumPy arrays. So if you do array operations like this, you'll get a Boolean array, which is all your trues and falses. And your trues and falses also count as 0 and 1. So if you do something like this and get a sum, that will tell you the number of trues that were in that array. So out of 1,000 pairs, 911 of them was the male subject or male sample taller than the female subject. And then if you want to make it into a probability, you just divide through by the length. And in this case, the two lengths are the same, so you don't have to make a decision about what to put in the denominator. Yes? Pairwise. Good question. Let me just repeat it. So I've matched up the two samples element-wise. I have not compared each one from one sample to all of the others. You'll get the same answer either way. It's mostly just a matter of sample size. And so I did 1,000 because that's close enough for what I want to do. But if you want to do more pairs, you could do it, or you could do the all pairs comparison, either way.
You could transpose and sort of make a matrix.
Mm-hmm.
Compare each one contains a sample to
Yep.
each item in the
Right. The suggestion is to make a matrix that does the all pairs comparisons. And you could do that. It would be efficient and fast and all that, but not necessary for what we're doing right now. But good stuff. Yes?
I know you're getting tired of my question, but
Not yet.
what a very efficient way of doing this would be, say, take the average male and average female and then go by some unit of standard deviation out. And that way you get a snapshot without having to use very much computational effort.
Good question. One option here is to do this analytically. In this case, we could do it analytically because the distributions are Gaussian or normal distributions, so there's a simple analytic solution. And yes, that would be efficient in the sense of faster than throwing computation at the problem, but fragile in the sense that it would break if I don't give you nice, smooth analytic distributions. One of the things I like about doing computation is that it's robust, the opposite of fragile, in the sense that if you now come along and you complicate the problem with lots of real-world details, I can handle that in a computational framework in a way that would break an analytic framework. Yes? Right. Oh, yes. And the other part of the answer is that this is fast enough for all practical purposes, so there's really no reason to optimize it. Okay. And have people got to this point yet? Have you read about Cohen's d, or should I give you more time to read and get to here? Have got to here already? Would like more time to get to there. Perfect, good, you're right on schedule. Okay, looking over people's shoulders, it looks like most people have got as far as reading about Cohen's d. I'll show you this interactive widget. How many people have used Jupyter interactive widgets before? Have you seen these? Have not seen these before? Cool. I think they're fun. And for data analysis, often a really nice way to get a feel for what's going on. In this example, we've got this statistic, Cohen's d, which is meant to be a measurement of the difference between two distributions. And it is in units of standard deviations. It's telling you that the difference in the means is, let's say, 1 standard deviation or 2 standard deviations. That can be a nice way to communicate a result, and for statisticians, they probably instantly understand that if two groups differ by 2 standard deviations, oh, okay, I know that that's a big difference. And 0.1 standard deviations is pretty small. But most people don't have a good intuition for Cohen's d. What this interaction lets you do is see the equivalence between d, probability of superiority, and amount of overlap. So I mentioned a minute ago that if Cohen's d is 2, and for the height of men and women, it's about 2, it's about 1.9. This gives you a sense of what that distribution looks like, how much overlap there is. This section in the middle is the percentage of overlap, and it is about 32%. And that corresponds to a probability of superiority of 91 or 92%. Probability of superiority is a problematic term, especially in this context, but I think of it as the junior high school problem, that if you line up a bunch of boys and girls and make them dance together, what is the probability that the male partner will be taller than the female partner? So. And in this case, it's about 91%. So one nice thing about those ways of reporting results, and this is getting back to the slides, these are a few different ways of communicating results that are comparable across different studies. So whether I'm talking about the difference between men and women, or the difference between any pairs of groups, animals or people or things that I've measured in the world, Cohen's d is portable across all of them. And it communicates an idea about how big the effect is in a way that's comparable. It's not immediately interpretable. The other things, probability of superiority and overlap, or misclassification, are useful, first of all, because they're probabilities, and so that's often useful information for guiding decisions. If you are doing a classification problem, and there's a cost of being wrong, then knowing the probability of being wrong is going to be useful for decision analysis. So probabilities are often good for guiding decision-making under uncertainty. Yes?
So if the distributions at play are like really non-Gaussian,
Yeah.
the tails are highly skewed,
Yep.
how would that inform the choices for describing their effect size?
Ah, that's such a great question. I'll repeat it. If the distributions that you're describing deviate from Gaussian or normal distributions, for example, if they have long tails or lots of outliers, how would that change what I'm doing here? And it's a great question because the answer is it depends. It really depends on the context and the audience. Sometimes you can get away with summarizing things. So a misclassification rate can be a good way to sum it up if the cost function doesn't depend on how much you're off by, right? But if it does, now I need a way to distinguish a near miss from being totally wrong. And if I assume that everything is Gaussian when in fact there are these crazy outliers, then I would be misleading my audience. So yeah, that one's hard. There's not a universal answer. A lot of it comes down to data exploration so that you understand what you're trying to communicate and then figuring it out how to convey it to an audience. Okay. We started with a difference in means. I want to talk about one other effect size, which is a difference in proportions. The moral of this story is going to be the same, which is very important to measure effect size, to express it in terms that make sense to your audience, but also there's no one perfect choice that achieves all of your goals. So I'm going to show you a couple of options and explain what I mean by that. And I'm going to motivate it by this study that came out a year or so ago. This one, by the way, has been replicated and did hold up under repeated testing. Really interesting result. I'm sorry you can't read it there. I hope you're following along on the slides. They studied the effect of giving peanuts to young children. and found that if you withhold peanuts, the children are more likely to develop a peanut allergy. And if they start eating peanuts young and continue eating peanuts, they are less likely to develop a peanut allergy. And the difference was quite stark, that the people who were not given peanuts had a 17% chance of developing a peanut allergy. And the ones who were given peanuts had a 3% chance. So it was the difference between 17 and 3. I should say this was a select group of people. I think they had been selected on the basis of some indication that they were prone to peanut allergies. So this is not the general population. But in this particular group, the difference was between 17 and 3. So right off the bat, intuitively understanding the context, we say to ourselves, wow, that's a big effect. Okay? But same question that we were dealing with before when we talked about the difference in means, how should we communicate this? One way to think about it is, what's the headline? If you only have one number that you want to convey, you want to measure the effect size in a way that's comparable across different studies and that people will understand, what's the one number that you would boil it down to? Let me put that to you for a minute. Again, chat with your neighbor and think about it. I suspect that you will come up with all of the ones that I'm about to show you. So no cheating and looking at the slides. Talk among yourselves. Think of different ways to convey the difference between 17% and 3%. Go. Okay, let me get a couple of ideas. I kind of tipped my hand by saying there is no right answer here. There are a lot of options, so give me some options.
I was critical of this because you don't know the sample sizes, and you don't know if the sample sizes are, if the groups are roughly equal or not.
Can I pause you for just a second? Because you're getting at the question that you're asking is about sample size and whether the two groups are equal in size. That's going to be relevant to precision, which is our second topic, which is how confident we should be about the effect that we measured. Right now, I just want to talk about how big it is. So let's stipulate for now that those two numbers are right, that 17 and 3 are the right numbers. All I want to do is summarize how big that difference is. Is that okay for now?
Okay, but you don't know how big the difference is unless you have the sample size.
Okay. Let me get some options for just describing the difference between 17 and 3.
I like taking the odds of the ratio, like 17
Yep.
versus 83, form that ratio,
Yep.
the logarithm of that.
Ooh.
3 versus 97, take the logarithm of that.
Yep.
And then just take the difference between those two logs.
Okay, so there are a couple of options. You mentioned an odds ratio, and you also mentioned a log odds ratio.
That way it works across like lots of scales.
Yes, and that has lots of good properties. Thank you. That's going to be one of our options. How about simpler than that? Yes.
Mine was less sophisticated, 17 minus 3.
And the answer was? 14. So one possibility is the simple difference in percentages. Yes? Right? The 17 divided by 3 is a ratio of probabilities, if you want to think of it that way. Yep.
To make a metaphorical ratio of probabilities, the 3% is roughly 1 in 30, 17% is roughly 1 in 6. So if you imagine a 30-student class of kindergarten, one of them is at risk versus 5 of them at risk.
Yes, good. Okay, so you're actually doing two things there that I liked. One was expressing the difference in terms of a ratio, but you're doing it in a really concrete way that people understand by imagining a room full of people and making it concrete and easy to understand. Excellent. Good. I think you did, in fact, get all the ones that I was going to mention. So one of them is a simple difference in percentage, just subtract. There's a 14 percentage point difference. This has the nice property of being interpretable. People kind of understand it. But the drawback that the percentage points are not created equal. The difference between 3 and 17 could be a really big difference. If it's the same size, but it's from 43 to 57, that doesn't seem like it's as big a deal. On the other hand, if there's like a 0.1 probability of dying, and you make it into a 14.1 probability of dying, that would be a very terrible thing. Yes? Good. Yes. Yes, let me paraphrase what you said, which is that knowing what the repercussions are is important. A small difference might be totally acceptable if you're talking about accidentally choosing a bad album, but less good if we're talking about killing children. Well put, yes. Killing children is in fact bad. If there's only one thing you learned today.
Thank you for setting me straight on both of my questions.
Good. So raw differences is one option. A percentage difference, which is you can say that if you administer peanuts to your young children, you will decrease their probability of getting allergies by 83%. And that's a nice number. It has a slight difficulty, which is that in this case, it's not clear what's the treatment and what's the control, because you could flip this around and say that if you avoid peanuts, you increase your probability by 467%. And they're both true, but they have different impact. People would interpret those different. One of the numbers is bigger than the other, and that's going to mislead people. So for a general audience, this is probably not a good choice. One option is to express things in terms of odds. And this is going from probabilities to odds. You can think of this as being the formula, that if someone gives you a probability in terms of p, it's just p over 1 minus p. But I really like the way that you expressed it a minute ago, which is, let's say that there's a 17% chance. The other half of that is 83. So 17 versus 83. And now just the ratio of those two, 17 over 83. That's the odds form of that probability. And in this case, the odds is 0.51. And this is the most common way that these things get reported in medical journals, is in terms of odds ratio. If you see OR as an abbreviation, that's what it looks like. It has the same problem we were just talking about a minute ago, which is that it is not symmetric.
But if you take the log, it becomes symmetric.
Yes, you're exactly right. If you take the log, it becomes symmetric. So when you express things in terms of odds ratio, you are still making a decision about what you consider to be the treatment and what you consider to be the control, and the number that you put up there will be different depending on what it is. Now, you'll notice that one of these is the inverse of the other. So 1 divided by 0.15 is 6.6. So if you know what you're doing, you can look at one of these and figure out the other one. And by and large, doctors are kind of used to thinking in terms of odds ratios, so they've got this figured out. But it's not symmetric. And the alternative is a log odds ratio, usually LOR. And this is just the logarithm of the number before. And in this case, it is now symmetric except for the minus sign. And this is very nice because it's symmetric, and very nice for other arithmetic properties. So if I tell you that you have multiple risks and they are independent of each other, then you can add up log odds ratios. They're arithmetic in that way. You just add them up. The biggest drawback of log odds ratios is just that people are not really familiar with them. So they're sort of like the axolotl in the sense that they're really cute, but kind of unfamiliar and a little weird. But they're also nicely comparable between studies. So if I tell you about multiple risk factors, like your probability of cancer, for example, and there are dietary factors and hereditary factors and other environmental, I could give you all of the log odds ratios, and you would be able to compare them, you could average across them, you can add them up. Log odds ratios have lots of nice properties. But they fall on the extreme end of this scale, where on the far left, I've got things that people understand, but that are mathematically problematical. And on the right-hand side, I've got things that are beautiful mathematics, and people have a harder time understanding. And depending on who your audience is, scientists, you're better off on the right-hand side. If you're a journalist and you're writing for a general audience, you probably need to think about the other side, or thinking along the lines that we were talking earlier, don't express them in terms of probabilities at all, but try to make it like a concrete example. 30 students in a room, here are 5 of them that will be at risk if you do or do not use this treatment. Good? Okay. So this is the summary of the first part, which is about effect size. And these are the 2 rules that I was mentioning a minute ago. You got to give me something that makes sense, that I can interpret. And again, thinking about the 2 other pieces of this, the confidence intervals and the p-values, effect size is the most important thing. If you only do one thing, tell me the effect size. All right. Now, I needed to check whether we actually have food out there. There are 3 parts of this, and it works out well if we take breaks at the middle points. Have they set up food? Not until 3. All right. We'll take our first break just to stretch out a little bit. We won't have food yet. We'll do the second part, and then we'll have food. So was that a question? Oh, okay. Very good. I will hang around and answer questions during the break, but why don't we take 10 minutes? I've got 2:25. Let's come back at 2:35. All right, we should get going again. So that was part one, measuring effect size and thinking about how to best express effect size to an audience. Now I want to get back to one of the questions that came up in part one, which is expressing precision. How confident should we be about something that we've measured? So here's an example. We talked about height. Now let's talk about weight. Let's say that you want to know the distribution of weight for adults in the United States, so you design the following experiment. You are going to do a telephone survey. You're going to pick a random number out of the phone book. You're going to dial that number, and whoever answers the phone, you're going to ask them, how much do you weigh? And you're going to write down the answer, and at the end you're going to make that distribution of how much people weigh. And my question for you all is, what could possibly go wrong with this experiment? So I want you to think of all the things that could go wrong, talk with your neighbor, and I'll collect answers in just a couple of minutes. Okay, let me start to collect some ideas. So I thought I had a pretty good experimental design. I thought this was going to be great. You people seem to think it's a terrible idea. So tell me about what could go wrong. Why is this a bad experimental design? I want to hear at least 10 things. People would lie about their weight. The sample might not be representative of the population.
Younger people probably don't have landlines, so they just don't find them in your sample at all.
Young people don't have landlines, so I wouldn't find them at all. People are going to make decisions about whether they are willing to answer the question, and that might depend on their weight. Yep.
People lie.
People lie.
I'm going to lie big. I'm going to give you a large positive number that's going to blow your standard deviation.
Some people are deliberately mischievous or malevolent.
You could get a European on the phone and get the
Could be in kilograms.
if the human's recording it, they're just recording wrong.
My person who's doing the survey might make errors when they write things down. Yep.
You don't know units, even if it's numeric, it could be ounces, pounds, grams.
There could be a miscommunication about the units. I'm sorry? Yeah, if the question's coming totally out of the blue and I haven't warmed them up, and if I have no relationship with the respondent, I might get less accurate information. Yep. Anything else?
We have a household with multiple people. One of them is going to answer the phone. Maybe that's going to always be the teenager or some other bias versus age.
Right, a household with more people in it. I haven't really, whoever answers the phone is who I'm going to ask. Good. I think, sorry, one more? Probably not going to get many kids because they don't answer the phone. Yep, right, young children. I think you've got many of the things that we get at. So there are a couple of pieces. So one is ideally, and I think somebody used the R word, representative. We want a sample that is representative of the population. What it means for something to be representative is that every member of the population has the same probability of appearing in my sample. And if that's not true, then I have some sampling bias. Now, I want to be a little cautious here. When you're critical of other people's experiments, it's easy to go a little bit crazy and point out anything that could possibly be wrong. It's not quite enough to say that if the sample is not representative, then it's going to be a problem. It will be a problem if the sampling process influences the measurement. So if I oversample people in red shirts, that might be okay. That might not be problematic, provided that there's no relationship between shirt color and weight. Okay? But if I oversample young people, that seems like there's probably a relationship between weight. If I oversample people who are more wealthy or less wealthy, there's a relationship between wealth and weight. So I'm going to run into problems there. So sampling bias is one of the issues. Here are a couple of ways that that could come up in my sample. People who, and this came up, household size. If you live in a big household, you are less likely to get selected, and that is probably related to wealth, and that in wealth is probably related to weight. And this is rule number one of all social science, which is that everything correlates with income, and therefore everything correlates with everything else. People have unlisted numbers, so maybe you're not going to get celebrities, you're not going to get rich people. Someone who's unemployed might be more likely to be at home when you call. Someone who has 3 jobs is probably not home when you call, and weight is related to all of those things. So sampling bias is one source of error. Measurement error is another thing that can go wrong. When you ask someone how much they weigh, you didn't say whether you went with clothes and shoes or not. Their scale might not be correct. They might not remember their weight. They might not tell you honestly what their weight was. It might get written down wrong, and it might get coded incorrectly. And in fact, I run into this. One of the big data sets that I work with is a great data set because the sample size is 300,000, but the data quality is not great. And in fact, there are a very large number of people in the country who are 61 centimeters tall in this data set. That's about 61 centimeters. On the other hand, there are a lot of people who are 6'1". That's 6'1". So I suspect that those are wrong. Okay, so sampling bias, measurement error. The other source of error is called random error, and this is just the random sample that you got. And I'm going to exaggerate. If you choose a really small sample size, like 3, you can imagine that just by chance, you get 3 heavy people or 3 light people. And so the size, the weight that you see in your sample might deviate from the actual population mean by quite a lot, just because your sample was small and randomness. Okay? So 3 sources of error: sampling bias, measurement error, and random error. In most real-world scenarios, sampling bias is important and large. Measurement error depends on the scenario. Sometimes it's important and large, sometimes it's not, if you're something that's easy to measure. And random error is usually the smallest and least important of the 3. However, random error has one thing going for it, which is that it is easy to quantify, and therefore it is what people spend all of their time concentrating on. And at the risk of spoiling my punchline, I'm going to tell you now, confidence intervals and standard errors measure only the third one and tell you nothing about the first 2. And the first 2 are more important and bigger in practically every real-world problem. So confidence intervals and standard errors can communicate a small bit of useful information, but don't forget about those other 2 things. All right, and as I said, common to ignore the first 2 just because they're hard to measure. Edward Tufte, the guy who did all those visualization books, actually tweeted this exact point not too long ago, and I grabbed his tweet. Random error is but one of 20 threats to learning from data. Disproportionate attention because it is only threat math model. It is the only threat that is math modeled. He left out a couple of words because 140 characters. All right, let's get back into the notebook. If you already got Jupyter up, you don't have to do anything other than click on the second notebook, which is sampling.ipynb. Read through it for a little while, and when you get to stop here, you should stop there. There's one. Okay, let me introduce a couple of things and give you a chance to ask questions, and then I'll let you get back into it. I want to give you a little bit of a setup for where I'm going here. The fundamental idea is that I want to estimate how unsure we are because of random sampling, and I'm going to do it by simulating a random sampling process. And I'm going to do it in 2 steps, and the first one is a little bit of a cheat, and then I'm going to explain the cheat, and then we're going to undo the cheat. Here's what the cheat is. I'm going to assume that we know the actual population distribution. Now, that's never true. If we actually knew it, we wouldn't have to do the experiment at all right from the beginning. But if we did, then we could estimate a confidence interval and a standard error just by running simulated experiments. So in this example, I am going to take this very large data set, the Behavioral Risk Factor Surveillance Survey, and use this as if it's the truth. So I'm going to assume that the distribution of adult weight for women in the United States is, in fact, that distribution. And just join me in stipulating that's the answer. Okay? Now, I'm going to simulate an experiment where I choose 100 people at random and get their get their weight. And now, for just the purpose of simplicity, I'm going to assume it's a perfectly representative sample. So everyone's equally likely to show up in the sample, and no measurement error, and none of those other problems. So the only thing I'm quantifying here is error due to randomness. And I'm going to do it by running the experiment a few thousand times. And every time I'm going to grab a sample of 100 women, take their average weight, and I'm going to take that sample mean and put it into a bin. Okay? So at the end of these simulated experiments, I'm going to have 1,000 sample means. And it's as if I ran the same experiment 1,000 times, and the answers are going to be a little bit different every time. And then I'm going to take all of them from the bin, and I'm going to make a distribution of sample means. Now, this is always a little bit confusing because this is not the average weight. And it's not the distribution of weights, it is the distribution of sample means. And it is called the sampling distribution of the sampling mean, of the sample mean. The sampling distribution of the sample mean. And what it says is, if I run this experiment over and over, how much do I expect the results to vary? And that's what the distribution is that you generated a minute ago when you ran this. So again, that is the distribution of weights. This is how much people weigh. They weigh somewhere between 30 kilograms and 120 kilograms. So this is a very wide distribution because this is the distribution of weight in the whole population. And that is not the same thing as the sampling distribution, which is here. This is, if I run this experiment over and over, how much would I expect the results to vary? And it says, if you get a sample of 100 women, n equals 100, then most of the time, the result will be pretty close to 72 kilograms. And that's good because 72 kilograms is the actual population mean. So most of the time, this experiment will work. The result, the estimate I get, will be pretty close to the truth. Obviously, that's what I want. So the location of this is telling me that this survey is unbiased. It means that on average, the error is about 0. That's good. Next thing I want to know is how wide is this distribution? And that's a measure of precision or lack of precision, which is the variability from one run of the experiment to the next. And it's not bad. What I see is that with n equals 100, which is a moderately big sample size, the range is from about 68 to about 77 kilograms. So it's not bad. And now there are a couple of ways that I can summarize that distribution. So again, that is the sampling distribution of the sample mean. And I could summarize that by reporting the standard deviation of that. Okay? And that is a measure of the width of the distribution. And my guess looking at it is that it's about 2 or 3 kilograms. I forget, you probably know the actual answer because it's one of the things that you computed in the notebook. Do you know? What did it work out to be? What is this? 1.63, is that right? It's a little bit lower than I thought looking at it, but that's probably just me being miscalibrated. There it is. So if you take all the sample means and compute their standard deviation, and this is one of those expressions that kind of makes people's heads hurt, but I'm going to say it and see how much sense it makes, which is the standard deviation of the sampling distribution is the standard error. And it's a measure of the width of the sampling distribution, which is a measure of how much the results will vary if I run the experiment over and over. And that's it. If you understand the last two sentences, you got the whole thing. You understand standard error, you understand sampling distributions. So let me say it one more time. The sampling distribution tells me how much my results are going to vary from one run of the experiment to the next. The standard deviation of the sampling distribution is called the standard error, and it's a measure of the precision of my estimate. Good? All right. Good so far. The next thing is a confidence interval, which you can think of graphically as being, I'm going to take this is my sampling distribution, and I'm going to lop off the highest 5% and the lowest 5%, and that's going to get me the middlest 90%. That middlest 90% is the 90% confidence interval. Eric? Ah, yes, we're going to take our break when we're done with this part. Thank you. All right. So that's confidence intervals. And here's what that works out to. It's from about 69.8 to 75.3 for this example. And then I've got some functions here that pull the whole thing together and make a representation out of it so that I can make this interactive widget. And this is a widget that lets me adjust the sample size. So I started out with n equals 100, and that means that each time I run the experiment, I'm going to sample 100 women. And this is the sampling distribution of the sample mean for that experiment. The standard error is 1.73, roughly. The confidence interval is 69 to 75. And now you can maneuver that widget in order to change the sample size. You should have a pretty good guess already about what's going to happen when you vary n. Large sample size, narrow sampling distribution. If you survey 1,000 women, the variability from one run of the experiment to the next gets to be quite narrow. And that means that the standard error is small, and the confidence interval is small. Flip side, if I go from 1,000 down to 10, the sampling distribution is quite wide. And that's just telling me that having only asked 10 people, I'm still quite uncertain about what the sample mean, what the population mean actually is. Yes?
There's one flip side. The larger sample, the craziest outlier gets crazy.
And so the flip side is for large samples, your craziest outlier gets crazy. Yes, save that thought, we'll come back to it. You're absolutely right. Okay, good so far? So that's understanding what the sampling distribution is and how you get from a sampling distribution to a confidence interval and a standard error. However, and this is the cheat that I mentioned, I started as if we knew the entire population, and we don't, because again, if we did, we wouldn't have to do the experiment in the first place. So now I'm going to tell you how we do this, even if we don't have that prior knowledge, and we're going to take the actual measurements, use the measurements to create a model of the population, and then we're going to use that model to generate lots of simulated experiments. And that's actually pretty much all there is to it, except that there are some different ways to make that model. So one of them is resampling. And this is a computational technique that is very simple, But it turns out to be really quite remarkable how well it works for how simple it is. But here's the idea. I'm going to take my original sample. I'm going to go and I'm going to run the experiment once. And so let's say n is 100. I now have 100 measurements. Now, I want to simulate what would happen if I went back and did that experiment again. One way to do that is to pretend that those 100 people really are the entire population, and draw a new sample from those 100 people. And my new sample size is going to be the same size as my old sample size. But I'm going to do it with replacement. So when I resample from my original sample of 100, it's possible that one of those people that I measured will end up getting measured repeatedly, sampled repeatedly. And some of the other ones might get left out altogether. So my resample is not identical to the original, but it is the same size. And it is, again, based on this assumption that those 100 people, those are the only 100 people in the world. If you know about Battlestar Galactica, it's exactly like Battlestar Galactica. There are only 12 Cylons, but there are many copies of every Cylon. So am I giving too much away if you haven't seen the show? Okay. All right. Forget the analogy. It is, if you don't know the show, it's both a spoiler and nonsensical. All right. Good. That's what resampling is. Get back into the notebook. The next section of the notebook takes you through a resampling process, and I'll meet you again at stop here. And I'll Okay, we should get back to it. If you're coming back from break, you want to get back into the notebook and especially get to this exercise. Let me try to remember which exercise number this is. This is exercise 1 for this notebook. So the example that we saw so far was all about the sample mean. It was all about figuring out the average weight. And we had the sampling distribution of the sample mean. Now I want to generalize that, and one really nice thing about this computational framework is that I can generate any sampling distribution you want. If you want the sampling distribution of the standard deviation, you can have that. You can have the minimum and the maximum and the median and the 10th percentile, whatever the summary statistic is. You're going to go collect 100 people, measure their weights, and then take the mean or the standard deviation, the min or the max. From a computational point of view, these are all equally easy. So this one computes the sample mean, and that is the sampling distribution of the mean. If I run this experiment over and over, that's how much it's going to vary. If I replace the mean with the standard deviation, it's typically around 17, and it varies between about 14 and 19. And the standard error is about 1.5. So I could report this, and I could say, I think that the standard deviation of weight in this population is about 17, plus or minus 1.5. Or I could give you that confidence interval. Or I could show you the whole distribution. Now this is, from an analytic point of view, this is becoming increasingly difficult. Like the sampling distribution of the mean is really easy to figure out analytically. The sampling distribution of the standard deviation, a little bit harder. The sampling distribution of things like median are actually pretty hard. But we can do it computationally in P dot median of the sample. But maybe I haven't defined that. Let me try percentile. Thank you. So the 50th percentile is the median. So this is the sampling distribution of the median. And you can plug in the 10th percentile or the 90th. And this is the point where people who are used to the mathematical approach to this kind of stuff start to freak out a little bit. Because these things from an analytic point of view are hard. But from a computational point of view, very easy. And that's nice, because often you don't just want the mean. You want these other statistics. So I think that's all we're going to do for now with that notebook. If you keep going through that notebook, I do pretty much the same thing in the second half, but I do it in an object-oriented framework. I think that can be a little clearer if you're used to object-oriented programming, but I'm not going to do it today for the tutorial, but you might want to check that out later on. So I want to wrap up the confidence interval stuff, the precision part, and then we'll get into hypothesis testing. So just to summarize, the way that you can quantify precision is by simulating the experiment over and over. And resampling is a way of doing that. What you do is you take the actual measurement and pretend that that's the whole population, draw samples from it, simulate the experiment, get the sampling distribution, and then you can report either a confidence interval or a standard error. Good, questions?
If you resample with a sample size, say, smaller than your original sample size,
Mm-hmm.
or larger for that matter, does that add or subtract anything from the way you analyze this?
Ah, good question. So if you want to simulate experiments of different sizes, you could do that. If your actual measurement is a small sample size and you extrapolate it out to a very large sample size, I think that's going to break down at some point. Yeah. Oh, and right.
Say my sample size is 1,000.
Yep.
Then I want to sample 100 to see
Yeah.
how my power changes over scale.
Great question. So if you have a relatively large sample, like 1,000, and you want to ask questions about what would happen if I scaled this down, and so drawing samples of 100 from a larger sample of 1,000, that would work very nicely. The question is, would I bootstrap or jackknife? And those are different ways of doing resampling. The one I'm doing here is bootstrap. Right, so the question is, I could, if I'm downsampling from a large one to a small one, I could take non-overlapping chunks or overlapping chunks. In the long run, they're going to work out the same, so there's not a strong reason to pick one or the other. Yes? Mm-hmm.
It could be a pretty rare sample. I mean, if you're really trying to say populations about, like, what kinds of sort of warnings do you give out?
Good question. So I'm really making a modeling move here. I'm using my real data to construct a model of the population. And you're right, if my original measurements were way off, and you mentioned because of bias, and you mentioned because of random error, but those are two reasons that my actual measurements might be bad, and that means that my model is going to be bad. And you were asking, what's the diagnosis for that? Am I going to be able to tell from looking at the results that that's going on? And in general, no. But this is not just a problem with computation. That's kind of an unavoidable problem. Yes? Mm-hmm.
Get a sample, and then from that example, use bootstrapping as you have indicated to replicate this larger, but it's the same group. I mean, what I'm trying to see is if there was any skewness in the original data,
Mm-hmm.
in any way, we kind of get this better represented in the sample size when we divide it and sample randomly from the different
Yes. Yes. So the question, let me try to paraphrase it, is if I've got my original sample and I'm doing any kind of resampling or jackknife, are there ways that I can, during the resampling process, can I try to deal with some of the biases that might have been in my original sample? And the answer is yes. There's actually one nice set of techniques that is based on an experimental design in which you deliberately oversample some parts of your population. And there are lots of reasons to do that. What you'll have then is, for every respondent that's actually in your sample, you'll have a weight associated with them. And that weight will tell you how much that person has been oversampled. And now when you do resampling, you can do weighted resampling, where you draw people in proportion to, for each respondent, how many people in the population does that person represent? And then you do weighted resampling. And that's a nice way of undoing the oversampling process. And you can do that as long as you have a model of what the oversampling process was, then you can invert that bias during resampling. But you need to have at least some indication. Good. Mm-hmm. Mm-hmm. Yes, could be. I'm going to have to stop there for now just to move on, but I like what you're getting at. Okay, I have a couple of summary questions for you. So one of them, just to wrap up, one of the things people get awfully confused about is the difference between standard error and standard deviation, because they both have the word standard in them. But they are very different things, and I've got a nice example to help you distinguish. So one of them is Frank Zappa. He is my model of a standard deviation, because he's kind of deviant. And this is standard error. Does anybody know what that is? That is Bill Buckner in the 1985 World Series, losing it for the Red Sox. So that is a standard error. All right, here's the key to remember. Standard deviation is a way to describe a population. Standard error is a way to describe an estimate. Okay? So the example that I have here is the average adult male height. The standard deviation in the United States is 7.7 centimeters. So that's telling me the width of the distribution. If I get a whole bunch of men and I measure their heights, the standard deviation of that distribution is about 7.7 centimeters. Now, if I collect a sample of men and I compute their average height, I'm going to tell you that the average is 178.5024 centimeters. And you're going to ask me, how precise is that estimate? You're asking me about the estimate, not the population, and I'm going to tell you, oh, it's an extremely precise estimate because my sample size is more than 300,000, and so my standard error is 0.00034 centimeters. That is a measure of the precision of the estimate. Okay? I chose this example because the sample size is really big, and as a result, the standard error is really, really small, much smaller than the standard deviation. Yes?
Are you at all disturbed by the fact that the standard error is much smaller than the precision of measuring people's height?
Ah, that's a good question. Am I bothered by the fact that the standard error is much more precise than the measurements? Yes and no. I'm not too worried about the measurement because as long as I'm rounding in a consistent way, I can actually measure the mean much more precisely than I measure any individual. However, there are other sources of error that I should be worried about, and I'm going to get to that in a minute. That's actually related to my next summary question. And that's this. So this is actually the same data. In my sample, again, 300,000 people, the average male height is this 178.5024, and that is actually the confidence interval that I computed. Now, my question for you is, what is the probability that the actual value falls in the 95% confidence interval? Okay. You're all shaking your heads, groaning, and telling me that it's probably quite small. And that is true. We really don't know. From doing this kind of estimation, we cannot answer that question. What is the probability that the true value falls in that range? There are two things going on here. One of them is kind of a theoretical thing. One of them is a practical thing. So if you know for sure that there's no sampling bias and no measurement error, and if the only source of error is due to random sampling, then there is a 95% chance that the actual value falls within that 95 confidence interval. Now, there are two problems with what I just said. One of them is the philosophical black hole about probability, which is that in classical statistics, at least the frequentist interpretation of classical statistics, you're not allowed to say that the population mean is a random quantity. The population mean is unknown, but not random, and blah, 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 blah. It all just goes into this huge black hole that is completely irrelevant to what I think is the real problem, which is that sampling bias and measurement error are pretty much inevitable in any real-world situation. And confidence interval, as I've said a couple of times, only accounts for random error. As your sample size gets really, really big, your confidence interval gets smaller and smaller and smaller, and that means that it is more and more likely that those other sources of error are dominant. So this is the irony of confidence intervals, which is that as the sample size gets big, your confidence interval gets small, and the probability that it contains the actual value goes to 0. And this is an example in this data set where that confidence interval is so absurdly small that it probably has no chance of containing the actual value. Okay, so not to beat a dead horse, let me just emphasize that last point again. Don't forget about other sources of error. Confidence intervals are not completely useless. They do quantify one source of error, and that's a good thing to do, but don't forget the other sources of error. We already took our break, so you don't have that one. All right, hypothesis testing again. I left this for last, and I'm going to give it the least amount of time because it is the least important of the things I'm going to talk about today. I agree with the psychology journal that banned p-values. I think if they were wiped from the face of the earth, we would all be better off for it. But you might be called upon to generate one, and you might be called upon to understand one if you're told what it is. So I'm going to give you a quick p-value 101, where these things come from. The logic of the whole thing, this is null hypothesis significance testing. It's actually not statistical significance testing. The logic of the whole thing is similar to doing a proof by contradiction. If you're coming from a mathematical background, you should be familiar with this idea that if I'm trying to prove that A is true, I can assume temporarily that it's false, and if that assumption leads me into a contradiction, then I have to conclude that one of my assumptions was wrong, and therefore A is true. This is similar. So I see something in a measurement. I see a difference between two groups, or I see a difference in proportions. And I think there might be something really going on there. What I can assume temporarily is that, nope, there's nothing going on. It's just a random effect. And I could ask, if this was just random, what would be the probability of seeing an effect as big as what I actually saw? And if that value is small, in other words, if my data are unlikely under the null hypothesis, then I conclude that the apparent effect is more likely to be real. So that's the logic of the whole thing. And let me send you back to the notebook. We're going to do a process here for hypothesis testing that's very similar to what we did a minute ago with confidence intervals. We're going to simulate the experiment over and over and count how many times we would see an effect as big as what we saw if, in fact, there's nothing going on. So take a look at the notebook. We'll take 5 or 10 minutes, and then we'll come back and go over it. let me give you a little bit of an overview of what's going on here, and then you can get back into the notebooks. So the two important ideas to get here are the idea of the test statistic, which is really hard to say, and the null hypothesis. So the test statistic is whatever the thing is that you're measuring that measures effect size. So this is kind of wrapping around to the beginning. If you think there's a difference in the mean between two groups, then the test statistic might be the difference in the means. Or it could be something like Cohen's d or anything like that. And you have a choice of what that's going to be. Often they are equivalent. So a difference in means or a relative difference or Cohen's d, for purposes of hypothesis testing, that's all going to work out to be the same. The other thing to think about is what this null hypothesis is, which is it is a model of the world where the effect that you think might be real is assumed not to be real. And again, if you think about it as a modeling decision, you need to go from your actual data to a model of the world that is, it's a generative model. It has to be a model that can simulate lots of possible worlds. In the previous example, we did that by resampling. So we had a measurement, an actual sample, and we drew from it with replacement. An alternative here, just to show you something a little bit different, I showed you a permutation test, which is a way of simulating the null hypothesis by doing random shuffling of your actual measurements, of the actual sample. So I've got two groups, and in this case, the question at hand is, are first babies more likely to be late? And this, if you've had children, probably came up in your lives at some point. It turns out to be mostly not true. But I wanted to explore this, so I got some data. And so I've got two groups, first babies and others. I have duration of pregnancy for the two groups. The actual difference between them is 0.078 weeks, which is about 13 hours. In a 39-week pregnancy, 13 hours is not a very big difference, although if you ask a woman in labor whether 13 hours is a big difference, you might get a different answer. But at least initially, it seems like a small thing. The question is whether that small difference might have happened just because of random sampling. And one way to simulate that is by taking the two groups. My null hypothesis is that there is no difference between the two groups. And if that's true, then I can just take the two groups and join them together into one great big jumble, and then draw samples from the great big jumble. And that's what the code does that you saw. So this is a permutation test. It's the reason, because shuffling is permutations. And so what you're going to get from this is the probability under the null hypothesis of seeing an effect as big as what you saw. And if that number is small, then that makes you think, this magnitude of effect is unlikely under the null hypothesis, that is, unlikely due to random chance, and therefore I'm starting to think that it might actually be a real effect and not due to chance. Now, I am extrapolating just a little bit beyond what is logically required. What I just said is true under normal circumstances, but there are pathological cases where it would not be true. So sticklers will object to what I just said, but under normal conditions, it's true. If you want the details of what are the sticklers objecting to and what is my response to the sticklers, feel free to read more. That's a link there that you can follow, but I don't want to get too much into it for now. All right, I have a diagram here. This is the picture that I want you to see, and then we'll get back into the notebook. This is the framework for doing this kind of hypothesis testing. What it says is I'm going to take my real data, and I'm going to compute a test statistic. In this case, it's the difference in means between two groups. And I'm just going to write that down. I'm going to use delta star to denote the actual effect size. Okay. Now, I'm going to go from my data to a model of the null hypothesis. And I'm going to use the model to generate lots of fake data. And that's what's going on here. So my model is generating lots of fake data. For every fake data set, I'm going to compute the same test statistic, and I'm going to accumulate this thing, which is the distribution of delta under the null hypothesis. It says, if in fact there's nothing going on but random variation, how much would I expect delta to vary as I run the simulated experiment over and over? This should be sounding familiar. This is very much like the simulated experiments we did for generating confidence intervals. The only difference is that I'm generating a test statistic, and now at the end, I'm going to draw a vertical line at delta star, which is the actual observed difference, and I'm going to compute the area under the curve there, which is the probability that the observed measurement would exceed delta star under the null hypothesis. And that thing is a p-value. Okay? And except instead of doing it analytically, I'm going to do it by counting. I'm just going to generate simulated data, compute delta, and count how many times delta exceeds delta star. Okay? Let me give you just a minute to get back into the notebook and see how that goes. I'll come around and answer questions so you can see how that goes in code, and then I'll run through it, and then we will wrap up. All right. If you understand this diagram, you understand hypothesis testing. This is really all there is to it. One of the reasons that I call this "there is only one test" is that this framework is all hypothesis testing. People will talk about, z-tests and f-tests and students t and all that. Those are all analytic shortcuts for going directly from the model of the null hypothesis to the distribution of delta. All the statistical tests, Wilcoxon's test and Mann-Whitney and Anderson-Darling and Kolmogorov-Smirnov, and every double-barreled test, they all do the same thing. They just use analytic methods to go across the bottom of the diagram instead of using computational methods to go up and around. And so you may now deallocate all of the memory space that you have used to learn about those tests and use it to store other important things, like the names of your children, their birthdays. All right. The computational framework, I'll just give you a quick run through of what's there. So this is the test statistic. This is the function that's going to take either real data or simulated data, and it doesn't know which is which. We're going to use the same function for both. You give me two groups, I will compute the difference between their means. That's all the test statistic does. And so if I take the actual data and compute the test statistic, that's delta star. That's the 0.078 weeks that I mentioned, which is 13 hours. And now the null hypothesis is that there's no difference between the groups. If there's no difference, I'm just going to glom them together, and that's what hstack does. That's just the NumPy command that takes two arrays and mushes them into one big array. And somebody asked me, well, does it rearrange them at all? No, it just lumps them together. But here, I've got a function called runModel that is taking that pool the two groups lumped together, shuffling them, and then splitting them up into two random groups by just taking the first n and the last m. And so my simulated sample sizes are the same as my actual sample sizes, and this will handle very nicely the case where n and m are not equal to each other, which I think you were asking about earlier. This is one of the nice things, again, about a computational framework, is that we can handle all kinds of weird stuff, like unequal sample sizes, no problem. Just as long as the model captures what's going on in your original experiment, you're good. So I can run the model over and over and get fake data. Every time I run model, I get fake data. I can pass the fake data to test statistic. So here's what happens if I run it once. I'll run it. And OK, this time it was 0.015. And the next time it's 0.099. Every time I run it, I get a different value. If I run it 1,000 times, I get an array of 1,000 possible values for delta. And if I plot that distribution, this is the distribution of delta under the null hypothesis. Sometimes it's small. Sometimes it's as big as 0.16. And delta star is the gray line that you can't quite see there. Delta star is 0.078. And you can see that under the null hypothesis, if there really is no difference between these two groups, delta is usually smaller than delta star. And if I count how many times it is greater, that is going to be this part of the curve. And it turns out to be about 15 times out of 100, which is my p-value, which is 0.15 or 15%. So intuitively, what that means is that if there's really no group, if there's really no difference between the groups, there's about a 15% chance that I could see an effect as big as what I saw. So if you think that that effect might be due to chance, that seems plausible. It is plausible that random sampling is the cause of this effect. That make sense? And that's it. That's all there is to hypothesis testing. Simulate the null hypothesis and count. Good? All right. Let me wrap up with a couple of things. So one of them is the interpretation of p-values. XKCD made fun of this because scientists have been kind of tweaking p-values for a long time. There's a magic number that I'm sure you're all familiar with, which is 5%. If your p-value is less than 5%, you declare statistical significance and publish. If it comes in at 5.1%, oh, that's a shame. Your experiment failed. You don't get to publish. You don't get tenure. And this, of course, is ridiculous. There's no difference between 4.9 and 5.1. If p-values mean anything, they only mean something in terms of order of magnitude. So if your p-value is like 0.01, like 1% or smaller, then yeah, it's unlikely that the effect is due to chance. However, it's still possible that it's due to bias. It's still possible that it's due to measurement error. You've eliminated one possible explanation of the apparent effect. That's good. That's not useless. But it doesn't really answer the question. Yes?
Isn't p-value really just a way of saying you need more data? If p-value is large,
Mm-hmm.
then that means that you just need more data if your effect size is real. Or it's not real. I mean, it's more
Yep.
about rejecting than accepting results.
Good question. So it's more about rejecting than accepting results. If the p-value is big, then your effect is plausibly explained by chance. And one conclusion is, I would need more data to demonstrate this effect if, in fact, there is one. That's true, and that is one way to interpret a negative result. You can go a little bit farther by saying, if the effect were so big, then with my sample size, I would have seen it. Since I didn't see it, I can put an upper bound on how big that effect is likely to be. Yes?
I remember hearing once that the number of experiments you do, the number of sample, number of trials, or
Yes, the question is about running multiple tests. And it's the idea that if you run lots and lots of hypothesis tests, and each one of them has a 5% chance of yielding a false positive, by the time you've run 20 tests, your chance of getting a false positive is approaching 1. And that is a concern. One of the ways to do that is to adjust the threshold and say, if I've done 20 tests, I'm not going to accept a p-value of 5%. I'm going to hold out for a much smaller value. And there are analytic ways of making that specific and concrete. Yeah. Yes, they're false discovery rate, yeah. And Holm-Bonferroni is one of the methods for doing correction for multiple tests. Yeah. Okay. The computational framework that we just used, one of the nice things about it is that you can plug in different models of the null hypothesis. You can plug in different test statistics. I won't do it now, but you can work through the rest of the notebook sometime if this is something that you want to get into in more depth. I showed this slide again. If you get this picture, you get hypothesis testing. I mentioned this. If you get a really low p-value, then it is unlikely that the observed effect is due to chance, but, sorry about that plosive, there are lots of other things that might be going on. Sampling bias, measurement error, confounding variables, fraud, honest mistakes, and on and on. So, to wrap up, from the beginning, I started by saying effect size is the most important thing. If you only tell me one number, just tell me the effect size, forget about everything else. However, confidence interval is a useful piece of information. It gives me a measure of the precision of your estimate, but I just have to remember that it only quantifies one kind of error, and there are other errors that might be going on. The p-value is another useful piece of information. It tells me whether the thing that you observed could plausibly be explained by chance, but again, I need to worry about other sources of error. Want to just point you to a couple of resources. So everything that I talked about is based on a couple of chapters from ThinkStats. This is my book about computational exploration of data sets. Most of it is not very theoretical. Most of it is very practical. It's the stuff that you do when you sit down with a data set for the first time and you want to see what's going on. Exploring variables one at a time, looking at relationships between variables, choosing visualizations, and doing things like regression and modeling of the data. So if that's something that might be useful to you, I do recommend it. It's, you can get a free version at thinkstats.com. You can download it there. If you would like a paper version, it's published by O'Reilly, and I have little tickets that will get you an author discount. If you're interested, I can give you some of those. I also want to acknowledge that this whole approach to statistics, this idea of effect size is important, everything else is less important, is partly based on this new statistics idea, which is not original to me. And this book is one of the original sources that really put these ideas down on paper. And then the last thing that we need to do before you all get to go is a survey. If you follow this link, you'll get a survey about this tutorial. This is, I have to say, very helpful information to us in future years when we're picking tutorials. Obviously, we want to offer tutorials that are good value and really useful stuff, so your feedback is very useful, and we appreciate it. Let me give you a couple minutes to work on that, and then I'll have a chance to take some questions and wander around. And I think that's it. Let me just say thank you all. I really appreciate you being here. This has been fun. Thank you.